Geometry in CAT is less about memorizing formulas and more about seeing structure inside a figure. This topic is really about converting a drawing into relationships, then turning those relationships into a quick answer. The fastest solvers do not stare at the page longer, they notice patterns faster. So the mindset here is simple. Every shape is a clue, and every clue points to a shortcut. The logic of geometry begins with a very practical sequence: figure, relation, formula, answer. First, mark the angles and sides that are visible. Then, look for symmetry, similarity, or any hidden proportionality. After that, apply the shortest useful formula rather than forcing a long calculation. Finally, verify through the options if needed. The exam insight here is valuable. Stop calculating blindly and start connecting visual dots. The real reason geometry matters in CAT is that visuals often process faster than algebra. A strong candidate does not wait to write equations before understanding the structure of the problem. Instead, the figure itself becomes the first source of information. That is also why rote memorization fails in twisted CAT scenarios. The question is usually designed to test spatial reasoning, not just memory. If you can see the pattern, you can usually solve it. This slide gives the mechanical core of geometry. For triangles, the area can be handled with the standard sine formula. For polygons, the interior angle sum comes from n-2 times 180. For quadrilaterals, diagonals and included angle often unlock the area. And for circles, sector formulas are essential. The parallel line section is also critical. Transversals create proportional intercepts, so ratios matter more than raw lengths. A classic exam habit is to hunt for a hidden 30-60-90 triangle because it often cuts the work in half. Golden rules of geometry are really habits of observation. Draw the diagram clearly and proportionally. Mark equal sides and parallel lines first, and look for symmetry before doing long calculations. Text constraints must be translated into geometric boundaries, not just read as words. Approximation also has a place when the options are enough to guide you. The key insight here is powerful. Your eyes often notice what your pen misses. A standard solution framework keeps the work controlled. First, identify the shape family, whether it is cyclic, regular, or some other known type. Then, fill in implied angles and lengths. After that, use the shortest specific formula available, not the longest one you remember. Finally, eliminate options based on visual logic. If you get stuck at step 3, the smart move is to search for similar triangles rather than forcing a new path. The topper's approach is very different from the slow, calculation-heavy method. Instead of chasing raw lengths, think in ratios. Similarity is especially important because it appears far more often than congruence in CAT-style geometry. Once similar figures are identified, scaling rules become your shortcut. Lengths scale by a to b, areas scale by a squared to b squared, and so on. The main habit to build is comparison, not computation. That is how problems get solved in seconds. This slide highlights some of geometry's strongest insights. If the perimeter is fixed, a square gives the maximum area. If the area is fixed, a square gives the minimum perimeter. Apollonius's theorem is a useful structural tool for medians in triangles. And the alignment of orthocenter, centroid, and circumcenter on the Euler line is another elegant pattern worth knowing. One warning matters a lot here. Never trust the diagram scale when the numbers disagree. In CAT, numbers are the truth. Speed in geometry comes from choosing the shortest path. Heron's formula is often the slow method when a simpler in-radius relation may work better. Likewise, an equilateral triangle's height does not need a long derivation every time. The direct formula is faster. Shortcuts like equilateral circumradius and cube body diagonal are exactly the kinds of things that save precious seconds. The lesson is not to avoid algebra completely, but to stop using algebra when geometry already gives you the answer. Advanced formulas become useful once the basic visual habits are in place. Polygon diagonals can be counted instantly with n-3 over 2. Polygon area can be expressed using perimeter and in radius. And the trapezium midpoint trick is a quick structural shortcut. The tangency relation PA times PB equals PC times PD is another high-yield result, especially in circle questions. The pro tip on this slide is worth remembering. One well-memorized slide can save several minutes across the paper. This cheat sheet puts the whole chapter into one compact revision frame. Alternate interior angles are equal. The sum of any two sides of a triangle is greater than the third. Equal chords subtend equal angles at the center. Cyclic quadrilateral opposite angles add to 180 degrees. And rhombus diagonals intersect at right angles. The final message is exactly right for CAD geometry. Be structured, be brave, and command the figure instead of merely reading it. That is the mindset that turns geometry from a fear topic into a scoring one. Circles in CAD are not about drawing a round figure and hoping for the best. They are about reading hidden structure with speed and confidence. The moment you see a circle, you should start thinking about symmetry, radii, chords, tangents, sectors, and the right triangle that is usually hiding inside the figure. This chapter rewards calm visual thinking far more than long calculation. So the real skill is learning to see the shortcut before you start working it out. The logic of circles becomes much simpler once you accept that every circle hides fixed relationships. Equal distances from the center, chords, arcs, and sectors all create patterns that can be converted into triangles. The most useful habit is to extract the triangle first, because once you have that, Pythagoras and ratio logic become available immediately. That is why circle problems often look complicated at first but become easy once the shape is broken into parts. Circles matter so much in CAT because they give you high-yield questions with strong accuracy potential. Visual logic often removes calculation errors, and that is a huge advantage in a timed exam. Even 3 or 4 correct questions from this area can make a real difference to your percentile. So this is a scoring topic disguised as a geometry topic. The big lesson here is that the student who sees structure will usually beat the student who only chases formulas. The golden formula in circles is really the Pythagorean relationship appearing in different clothes. A radius, a perpendicular, and a chord often combine to form a right triangle, and that is where the real computation begins. The slide also reminds you that many diameters are hidden as diagonals of inscribed shapes. So the figure may be giving you more than it appears to at first glance. One strong exam habit is to always look for the hidden 30-60-90 or 45-45-90 triangle before doing anything else. This setup is very clean if you read it the right way. The chord is given as 24 centimeters and the radius is 13 centimeters. So those two numbers are your starting anchors. The question is asking for the distance from the center to the chord, which is the perpendicular drop, that unknown d shown in the diagram. The moment you see a chord and a center, the instinct should be to split the chord into 2 equal parts. So each half becomes 12. That instantly gives you a triangle formed by radius 13, half chord 12, and the unknown distance from the center. This is the classic circle setup where the full chord is 24, so the half chord becomes 12. The radius is 13, and that immediately tells you to form the right triangle from the center to the chord. Once the perpendicular bisector is drawn, the triangle is clean. One side is 13, one side is 12, and the unknown distance is d. From there, the relation becomes 13 squared equals 12 squared plus d squared. So the structure of the problem is completely clear. The bigger lesson is that a neat sketch saves you from algebraic confusion, because the moment you see the 13, 12, and 24, the answer path is already visible. Here's where speed comes in. You already have radius 13 and half chord 12. So this forms a 5, 12, 13 Pythagorean triplet. That means the perpendicular distance is directly 5 without solving the equation step by step. The whole point is to recognize the pattern early. Once you see it, you skip the algebra completely and finish the question in just a few seconds. Exactly how toppers approach it. This section gives you some of the sharpest edge cases in circle geometry. A semicircle always gives a perfect 90-degree angle, which is a powerful clue for building a right triangle. In cyclic quadrilaterals, opposite angles add to 180 degrees, and that becomes the quickest trap to check when a shape sits inside a circle. The deeper habit is to stop trusting appearances and immediately test whether the figure contains a hidden right angle or cyclic angle sum. Speed matters a lot in circle problems. And here we can see why direct symmetry beats long quadrant algebra. For external tangents from a point, the tangent lengths are equal. So PA equals PB is the clean shortcut. That instantly gives you congruent right triangles and removes the need for cumbersome distance formulas. This is the kind of trick that turns a 5-minute calculation into a 3-second recognition problem, which is exactly what CAT rewards. Advanced formulas become very useful once the visual basics are in place. The distance formula here is framed as Pythagoras with coordinates, which is a nice way to connect algebra and geometry without treating them as separate worlds. The horizontal and vertical components, delta x and delta y, make the geometry of motion or displacement easier to handle. The exam insight is simple but strong. When a shape is placed on axes, you are really translating a geometric problem into a coordinate one. The cheat sheet brings the whole chapter together in one compact revision map. Tangent is perpendicular to radius. Semicircle angle is 90 degrees. Cyclic quadrilateral, opposite angles sum to 180 degrees. Equal chords subtend equal center angles. And the hidden right angle triangle should be your first search pattern. The final note is exactly the right mindset for CAT. Do not just look at the circle, command it through logic. That is how this topic becomes a reliable scoring area instead of a time trap.